Crystals are not alive, but mimic life in many ways, including growing. And yet, on distant alien planets, could life have grown based on crystals? We've discussed some alternative chemistries and solvents life might operate under besides carbon and water, such as ammonia or silicon, and many others have been suggested, but one popular option we see in science fiction a lot is life forms made from crystal. We had the crystalline entity from Star Trek The Next Generation that devoured Lieutenant Commander Data's homeworld, for instance, and many more examples in sci-fi. But crystalline life represents some interesting challenges and options, so I thought it would be a fun topic for our monthly Nebula exclusive. We'll explore some of the ways this might be possible, then we'll take a visit to 5 planets with 5 very different and harsh environments, and 5 very different types of crystalline ecologies: Vulcan, Ribbonworld, Longenacht, Telluride, and Tempest. Now, in the past, we've focused on a specific element or molecule, like silicon or ammonia, as a substitute for the existing structure in terrestrial life, or that existing basic solvent that chemistry takes place in, like water. Silicon replaces carbon as a scaffold that more complex organic molecules get built around because it has similar properties. Ammonia replaces water as the solvent chemistry takes place in because it's another good solvent that's also plentiful in the universe. Crystal-based life is a little more complex though, because we can't just plug it into our vision of existing life. Crystals are also an incredibly broad category of materials, whose common denominator is that they form relatively simple patterns in 3 dimensions from some atoms or molecules. At the large scale, this tends to be visible as sharp angles and flat surfaces, and often a transparency to light. This orderly arrangement of atoms, molecules, or ions extends uniformly in all 3 spatial dimensions, contributing to the crystal's unique physical properties. The formation of crystals often occurs through natural processes such as the cooling of a liquid or the slow evaporation of a gas, leading to the gradual organization of particles into a repeating pattern. This process can happen in various substances including minerals, metals, and even organic compounds. Indeed, one of the best known is sugar crystals, and sugar is certainly an organic molecule. The specific pattern of a crystal lattice, which defines its symmetry and structure, is crucial in determining its physical and chemical properties. There are quite a few lattices, but the most common ones are the face-centered and body-centered cubic lattices and the hexagonal close-packed. Generally, they do represent the most tightly packed arrangement of particles you can make, and as an example, if you have a bunch of coins the same size, your tightest packing is going to be one with 6 more arranged around it in a hexagon, and expanding beyond that in the same hexagonal packing. And 91% of the area will be filled that way, but this will vary a lot if you have 2 different types of coins or what their ratio is. When we're making these from atoms or molecules, it can result in a lot of very interesting properties, some of which we would think of as either quasi-organic or plausible basis for life, and semiconductors might be a very good example of that, which we'll return to momentarily. But I should get the conversation started by saying that a crystalline life form is a broad concept. For one thing, an organism need not be entirely crystalline to qualify, given that the minority of atoms in our body are carbon. Nor should we be calling something crystalline life just for having some crystals in it, since we would then qualify too. So we want to be looking at cases where a large portion of the organism is crystalline, or where some vital feature is. This is easier for the idea of a mobile alien, as while we might imagine a big monolith of crystal on some lightning-racked planet being essentially a natural computer, using crystal for muscle and mobility is a bit harder. Not necessarily impossible though. All muscles approach motion essentially as a ratcheting system, pulling taut or relaxing to move the more rigid endoskeleton we've got. And we could have a critter with a crystalline skeleton, but it is worth noting that there are some organic crystals like naphthalene diamide that have flexibility by having stacked layers that bend or slide, and thus might allow flexible and mobile structural joints. Though again, we might simply have a creature whose skeleton was crystal, or whose hide was. Our bones are not simply rigid structures that you can just casually replace with metal pins or rods. They are involved in the production of our blood cells, which are most of our cells, as well as storing and releasing of minerals and fat. But those do not have to be included on a life form, or could be served by some other organ. Something more amoeba-like might learn to secrete crystals as a bunch of bones or exterior scales, or like crabs, go and get the discarded ones. Indeed, in Brandon Sanderson's excellent Mistborn series, there is a shape-changing species that is basically a blob that will steal discarded bones from humans, or even animals, or a mix of many of them to give themselves a skeleton, and some of the more sophisticated creatures instead have artificially crafted skeletons made from crystal. This is probably our low-hanging fruit of crystal life forms, since it's very easy to imagine a creature developing a crystal skeleton, especially given that the inorganic part of human bone mineral is already constituted of a poorly crystallized hydroxyapatite of calcium phosphate, which gives them their rigidity and strength. The real question isn't if it is possible, but if this is going to give a skeleton or protective plating better than other options available, as otherwise they might just evolve a normal skeleton of bone after a while, even if they started as crystal. This would depend a lot on the native environment though, as while crystal tends to be brittle and rigid, as we already noted there are exceptions, and moreover, a lot of substances we think of as flexible are not when in a colder environment. So too, some wouldn't even be able to exist in a hotter environment, while a crystal such as quartz or dolomite can handle temperatures that destroy normal life. It may be that a hypothetical crystal life form might fare better in an Earth-like environment than we do, but regardless, there are many environments where we could not exist and they could. High-pressure ones particularly come to mind. There's also the matter of energy flux and storage, which are critical aspects of life. You can't have life, especially complex and robust life, without a lot of energy transport going on, or energy flux. The sun is our main one for Earth now, but in the past before photosynthesis, our planet's volcanic vents are thought to have served that role in a lesser capacity, though one that also allowed a nutrient-rich bath near where the energy was coming in, much as coastlines or rain on topsoil does. This could include deep subsurface oceans churned by volcanic or tidal forces, allowing even frozen moons around dimly lit gas giants to potentially host life. As we noted in ammonia-based life forms, ammonia is a solvent that's nearly as good as water in most respects, better in a few, and nearly as common in this universe as water, unlike some other possible liquids like quicksilver or molten magma, which is common enough but rough on most complex molecules. But because water is such a good solvent, it also makes life hard, meaning you need to wrap your organism in a waterproof outer layer, and means any of your energy storage either needs to be in such a protective layer or hydrophobic like fat cells are. Sugar obviously dissolves in water quite easily, so any organism producing sugar to live can't just pile up sugar crystals somewhere like we do in our artificial sugar refining processes. Sugar dissolves well in polar solvents like water, ammonia, or methanol, but does not dissolve in non-polar solvents like gasoline or diesel. Putting sugar in someone's gas tank is a well-known prank that, like cow tipping, has a lot of urban legend around it. Sugar can clog the fuel filter and cause damage, but this is from the sugar not dissolving and clogging the filter. Various alkanes like pentane, hexane, heptane, and aromatics like toluene, benzene, and xylene are not polar solvents that you could have large pockets of on some planet, and in which a life form might opt to use sugar crystal as an energy storage medium. And while you could find a lot of that in crude oil, which is the byproduct of life on Earth, we do find many of these substances occurring on seemingly lifeless worlds, particularly methane. And this is just sugar. Many crystalline substances might dissolve in other common solvents and at different rates and saturations. For me, this summons the image of a sugar monster alien roaming the subsurface gasoline seas of some icy dwarf planet like Pluto, or giant sugar ants roving the megahives of some tidally heated moons. And these are certainly intriguing options, though I would not place wagers on their likelihood. We might imagine this as a subset of life forms, sugar or candy aliens. It is easy to imagine a predator-prey cycle developing that way, or 9 out of 10 dentists recommending such planets be quarantined. Life can take many forms, organic, mechanical, or even crystalline, but no matter the form, all civilizations are shaped by the limits of knowledge. Could there come a time when even the most advanced species, be they carbon-based or crystal-bodied, run out of new discoveries? In The End of Science, our Nebula exclusive episode, we explore the ultimate limits of knowledge and whether scientific progress might one day come to a halt. What happens when there are no more fundamental mysteries to uncover? Would civilizations continue to thrive, turn to philosophy, or simply stagnate? Could the greatest challenge for an advanced species, crystal or otherwise, be the burden of knowing everything? Join us in The End of Science, available only on Nebula. Nebula is the largest creator-owned streaming platform where every SFI episode airs early and ad-free, alongside exclusive content from myself and many other fantastic creators, like Real Engineering, Simon Clark, and Joe Scott. And check out Joe Scott's look at strange life on distant worlds. The first humans on Mars will not be humans. Sign up at go.nebula.tv/IsaacArthur using my code IsaacArthur to get 40% off an annual plan, $3 a month. Nebula also offers lifetime memberships and gift options so you can share exclusive content like The End of Science with friends and family. And for new Nebula subscribers, you can get access to guest passes. Share your passion for Nebula with friends and family. With them, they can get free and easy access to all Nebula content for a whole week. So go subscribe to Nebula and give a week of exclusive content with guest passes using the link below to get 40% off the annual plan. And now, let's return to the mysteries of crystalline life and alien evolution. However, while imagining alternative chemistries for photosynthetic life, or weaker ecosystems running on tidal or geothermal energy is interesting, crystals can be used for direct sunlight conversion into electricity. This is what solar panels are, as well as for energy storage. Lithium-ion batteries have a cathode made of a lithium cobalt oxide crystal, and we have some new ones that use lithium and sulfur. There's likely to be many that store energy less efficiently too, which might pop up naturally. That said, crystals storing energy tends to be a common theme in science fiction with a dubious connection to reality. I remember in one of the Season 1 episodes of Babylon 5, set centuries in the future, Mr. Garibaldi is trying to build a motorcycle, and his alien friend Lanier replaces the gas engine with a Minbari energy crystal. I quite enjoyed that episode when it came out when I was 13, but even then I knew enough science to wonder about that, and also wondered why no one had motorcycles in the future. Now it is something of a B-plot filler for the main story of the episode, as well as a blatant product placement for that motorcycle company, and there was also a particularly hot period for the magic power of crystals, so it's not too surprising, and we see that with the dilithium crystals of Star Trek too. Or the kyber crystals used for focusing in Star Wars lightsabers. And there at least there's some scientific basis for the concept. We did and do use crystals for focusing light beams. What exactly dilithium crystals do, given that they are entirely fictional, has tended to be vague and inconsistent and full of technobabble. And this stands to reason if you're trying to imply an energy storage or generation capacity orders of magnitude beyond modern batteries or chemical fuels. We could hypothesize something weird like a given crystal lattice being good at slowing neutrinos down so they can be absorbed by normal matter and causing a small nuclear reaction as a result, but otherwise crystals wouldn't tend to be any better at storing energy than any other chemical or battery rig-up, nor do they need to be for the purpose of biological life. Though again a lot of batteries do use thin sheets of crystal substances as layers. Alternatively, they are very good options for power generation, in that even a primitive semiconductor solar cell is more efficient than the C4 photosynthesis process, which is the most efficient of the photosynthesis processes we have. There are organic semiconductors and naturally occurring semiconductors, and it isn't too hard to imagine an organic solar cell emerging. Silicon is not the only element you can make semiconductors from. Indeed, this year is the 150th anniversary of Carl Braun discovering and documenting the first semiconductor diode effect, and that was between a simple metal point and a galena crystal, which is a mix of lead and sulfur and the main ore for lead, and one that you can smelt out in an ordinary wood fire. Maybe some simple life form might emerge on a hotter planet where metal veins and galena crystals were common and exploit that. Certainly, silicon is common enough in the universe, and prone to floating up in rafts on magma, so likely always be common in planetary crusts. For us it is biologically inert, but a different chemistry might use it, and there's also nothing stopping an organism from evolving to use that inert silicon as a nice protective outer layer alternative to scales or skin. If ever an organism evolved a natural solar panel and a way to use and transport that generated electricity, which is not a big jump either when you contemplate neurons and nerves, then that's going to be one of those evolutionary avalanche events like photosynthesis or oxygen breathing that reworks the entire ecosystem as that develops and diversifies. It might allow a much higher amount of biomass and activity than even photosynthesis on Earth does too. The bigger your ecosystem and the faster it runs, the faster evolution in general is going to go, and loosely speaking, the bigger your food chains. One interesting thing though is that while photosynthesis is taking sunlight to produce sugar as a fuel you can consume then or later on, the photovoltaic effect and solar power just produce electricity, not a fuel you can burn, or rob by eating the plant and stealing its sugars, or eating the animal that ate that and stealing their fats and proteins. So if you didn't have a particularly good and efficient way to store that energy, you could end up with an ecology that was running heavily on electricity during the daytime and use that process only for limited battery storage, which isn't super efficient normally. They might not have a normal predator-prey cycle since you're not trying to eat each other for energy then, just steal nutrients, which might be concentrated in that organism or to eliminate competition for sunlight. Of course, they might evolve a decent chemical battery, they're not tricky or problematic with biology, or take advantage of something like thermal heat storage. For that matter, we could also imagine organic or crystal thermophiles evolving to generate electricity from heat, or simply electric heaters to produce heat that might then be returned as electricity, albeit at low efficiency. Let's wrap up by imagining 5 worlds on which some crystal life popped up: Vulcan, Ribbon World, Longenacht, Telluride, and Tempest. On the planet Vulcan, whose bright sun began going subgiant millions of years ago, all the water slowly boiled away, leaving a hot planet with a thin and toxic atmosphere of heavier chemicals, particularly sulfur, which often caused crystal formation on the landscape below. There's no animal life bigger than an insect, but there are vast crystal structures on the hazy edge of life itself that generate energy for the ecology hiding under them. Here, as the sun rises through the chemical haze, life bursts into activity, powered by the photovoltaic crystalline structures dotting its surface, and hiding inside them and tunnels near them that remind explorers who found them of the early Martian colonies in their domes and tunnels. While the insects here are not very similar in basic biology to terrestrial bugs, they have crystal endoskeletons of a wide variety of hues and use a great deal of bioluminescence in their communications. On the Ribbon World, a tidally locked planet near its dim red dwarf sun, life evolved in those eternal twilight seas on the unmoving day-night terminator. The planet's orbit is somewhat eccentric and causes a good amount of tidal activity and thermal events in those twilight seas. In time, some life adapted to the eternal sunlight of the day side, which varies little over time, merely by location, and as it grew ever more arid near the hot center where the sun is at constant noon, life adapted to move away from using water as much in favor of growing various crystalline structures from the abundant silicon there. While scientists believe these two types of life had a common origin in the distant past, they are very unalike. But what's interesting in the last few million years is that this dayside electric plant life has learned to be more tree-like in its existence, grown tall and with canopies to compete with neighbors for sunlight. Moisture has begun to be able to move back into these crystal forests and jungles to allow life from the twilight sea to adapt itself to live there too, under the rainbow-lit forest canopy. On the moon Longenacht, there is very little tectonic activity anymore, as it was once a large and geologically active moon, but slowly cooled and tidally locked. Life evolved earlier there, and its now thin but still present atmosphere used to be thicker and helped slow down that tidal locking. It now has long days and nights like our own moon has, but the photovoltaic life that adapted there to make use of silicon and metals to make organic solar panels and wiring also evolved natural thermal wadis to store heat for later power generation. They grow large hollow and insulative crystal balls beneath them and fill them with materials with a good thermal capacity, in which they grow roots of conductive wires and thermopiles to send electricity to turn into heat that they then reclaim as electricity by thermoelectric effect during their long nights. On the planet Telluride, there is a thick crust over magma that tends to have lots of pockets of different materials and densities, and here we have a microscopic organism that evolved to tunnel between various pockets, and at one point left a lot of bismuth telluride crystal in its wake, a common thermocouple material. No large animals ever appeared on this planet, but while these microorganisms grew and diversified, they left in their wake lots of large networks of tunnels lined with these thermocouples and other conductive metals that electricity moved along, and these developed into neural networks and even simple brains in some places, able to send signals to each other on the wider and somewhat ragged planetary grid. These are very spread out neurons, but also very high-speed ones, resulting in millions of modest brains and several thousand mountain-sized brains spread over the planetary crust that each roughly match human intellect. Over the eons, they've learned how to prod the various microbes into performing this or that simple activity for a very limited control over their environment. On the planet of Tempest, the sun never shows its face, though you can see the sky brighten or darken slightly over the course of its 12-hour day. Storms rage across the world constantly, mostly west to east, tearing up dust and mud and depositing sediment as they go, and the volcanically active world spews new volcanoes and metal ores at an impressive rate. Sometime in the past, a very complex mix of electric conductor and crystal formed that can grow as thin, lightning towers, thin as they are north to south but long from east to west and quite tall. They absorb the numerous lightning blasts and release in turn a slow, dimmer glow. Scientists aren't sure if the lightning towers are alive. They have complex natural superconductors running through them that some think might be a simple neural network, but others argue it is merely a natural way of spreading the lightning energy around. Many of these lightning towers have even developed a variety of core-like lifeforms on their outside, which dig in pockets and baffles in which small ecologies thrive, deriving nutrients and moisture from the mud-laden storm that passes by. In the end, it is hard to say if a life based heavily around crystals might be able to evolve naturally, but I think we've given some food for thought as to some paths it might take. And of course, whether something can evolve or not is very different than if we can engineer it. So perhaps we will find planets like Vulcan, Ribbonworld, Longenacht, Telluride, and Tempest out there among the stars, with strange alien life already on them, and if not, perhaps we might create such life one day. And on that note, thanks again for joining us for our monthly exclusive here on Nebula.